In our last lesson, we gave a general overview of NMR, focusing largely on how to identify how many signals a molecule should give, and also what locations those signals will show up. In this lesson, we'll focus on how to tell how many protons a signal represents, and also how to use NMR spectra to give information about neighboring nuclei, other hydrogens nearby. We'll also talk about carbon-13 spectrum. In addition to getting information about the number of heterotopic protons, we can integrate each peak. The integration of peaks gives ratios of protons of each type. Since modern instruments are connected to computers, this is always done digitally. So we see an integral trace that shows a horizontal line where no area is added onto the curve. You see that shown in blue. And then the trace rises across each peak in accordance with the area that's under the peak. We can then use the height, the difference between those flat sections, in order to determine the ratio of proton types. This paraxylene has two types of heterotopic protons. The CH3 groups are distinct from the benzene protons. Since there are 6 CH3 protons, but only 4 benzene protons, the signal trace represents the CH3 protons, representing the CH3 protons, is 1.5 times as high as the other peak. You can see that on the integral trace. Notice that this only gives the ratio, so that while it's actually a ratio of 1 to 1.5, it could actually mean 2 to 3 or 4 to 6 or many other actual values for protons. Integration is an essential part of proton spectra, but the very small portion of carbons that are actually carbon-13 make it impossible to integrate. So we've mostly focused on NMR. A lot of what we've learned has applied to carbon-13 as well. In this case, it doesn't. We can't integrate carbon-13. The final part of our NMR puzzle is that since each proton is essentially a magnet, these magnets can change the field that's felt by neighboring nuclei. If we look closely at the structure shown, we can see that we have 2 heterotopic protons, the proton on the carbon with 2 chlorines, and the protons on the carbon with only 1. But we see more than 2 peaks. Each peak is split into several slightly different and smaller peaks by the magnetic effects of the other nuclei. So here's how this works. We have every nuclei having the possibility of 2 different magnetic states. Each nuclei can create 2 slightly different effective magnetic fields for its neighbors. So each neighbor will couple to create a split signal. How close the nuclei are determines the strength of the split. So the only neighbors that typically actually split on a range that we can see are those separated by 3 or fewer bonds. And so practically this means hydrogens that are on neighboring atoms, hydrogens on carbons that are connected to each other. We can count up the neighbors, and the number of neighbors will always tell us the number of peaks. If we have no numbers, we always have 1 peak, just as we saw in every example before today. If we have any numbers, we will see 1 more peak than the number of neighbors, a rule that we call the n+1 rule. So if we have two neighbors that are nearby, we should see 3 peaks, and we'd call that a triplet. This makes sense if you think about how each additional neighbor will split the peak. On the left, we see a neighbor give 2 possible changes to the magnetic field. One so that it increases it, and the other so it decreases it. So we see 2 peaks. In the center, we see a triplet that occurs if we have 2 neighbors. Now we have 3 possible states, both of the neighbors increasing the signal felt, or one of the neighbors increasing while the other decreases, or both decreasing. But since there are 2 ways to have one increasing and one decreasing, we see twice as much signal. And so the center will have 2 for every 1 on the outside, a 1 to 2 to 1 ratio. On the far right, we see a quartet from 3 neighbors, now with 4 possible states that are either adding all together, 2 adding and 1 subtracting, 2 subtracting and 1 adding, or all subtracting. And since there are 3 possible states where 2 are going one direction and 1 the other for each of the directions, we see a 1 to 3 to 3 to 1 ratio. The ratio of peaks is predictable, as the peaks overlap in the same way that Pascal's triangle is built up. So each new entry is the sum of the values above, with the outermost values always being 1. So the row that's after the 1 to 3 to 3 to 1 ratio that we just saw would here have a 1 to 4 to 6 to 4 to 1 ratio, because the 4 is the sum of the 1 and 3 above it, and the 6 is the sum of the 3 and 3 above it. If we look at the next row, even though it's not show, a hextet would be a 1 to 5, the sum of the 1 and 4, 10, the sum of the 4 and 6, 10 again, and 5 and 1. And so we can build this up however long we need to. So to check your understanding, let's try to build up what we'd expect the NMR to look like for this molecule. First, we start off by trying to identify how many heterotopic protons. Pause and try to identify for yourself how many there'd be. We should have seen 3 heterotopic protons. We should see one type of proton here, we'll call that HA, and there are 3 of them on this carbon. This carbon has just 1 hydrogen, we'll call this HB. And then these carbons each have 3 protons again, we'll call these HC. But both of these carbons are identical to each other, and so both of these sets of hydrogens are identical as well. Now that we've identified what number of distinct hydrogens there are, or how many heterotopic protons, try to identify which things will shift the most. HA, HB, or HC, which would shift the most? If we look at the different protons here, HA is connected directly to an oxygen, but it also has hydrogens attached to it. HB is also attached to the same oxygen, but it has the more electronegative carbons instead of hydrogens. So HB should be the most shifted because it has the most electronegative things attached to it. After that, we'd expect HA, and then HC should be the least shifted. So we should see HB show up the most downfield from 0 parts per million, our reference peak. And then after that, HA and HC should show up the most upfield. The last part of what we've talked about so far is what type of splitting would we expect. So we're looking for protons that are within 3 bonds of each other. So if we think about HB, HB is 1 bond to this carbon that it's attached to, another bond gets us to another carbon, and then a third bond gets us to any of the HCs. So HB should be split by those 6 HCs, and we should see a heptet or a septet. 7 different peaks, because 6 peaks will split, or 6 neighbors will split us into 7 peaks. If we look at HA, HA doesn't have any neighbors other than itself that are within 3 bonds, and so we should see a singlet for HA. And finally, we have HC. HC should only be split by HB. There's only 1 HB, and so we should see HC show up as a doublet. In some cases, it actually looks like the N+1 rule is violated. So take this example of ethanamine. Ethanamine has 3 peaks, one for the NH group, the next one to the right is from the CH2 group, and the farthest right is from the CH3 group. The CH2 group in the center shows up as a quartet, indicating it's split by 3 neighbors, only from the CH3. It doesn't show any splitting from the NH. Likewise, the CH3 group that's shown on the far right only shows up as a triplet, indicating the 2 neighbors, so it's being split by the CH2. So the amine NH2 protons and the CH2 protons don't appear to be coupled together, even though they're close enough that they should split. And that's because protons on nitrogen and oxygen will always be undergoing hydrogen bonding. And because they can hop from one nitrogen to another, we don't actually see good splits. The same reason that they're broad is the reason they don't split neighbors. That's something to look out for. If you do want to remove the nitrogen peaks, if you want to see how many are coming from NH or OH, you can actually do that using deuterated solvents that can exchange. Then you end up with a deuterium, which is not active in NMR. So we could use like D2O instead of H2O as a solvent, and we see that disappear. Again, the hydrogen bonding is always faster than NMR acquisition, so we're always going to see an average singlet for things that are in the NH or OH range, and we'll also see an average for those not splitting any more than the other peaks would already be split. We had talked before about how all the shifts should end up being exactly the same no matter the strength of the instrument. That's actually a little bit different than what we see when we're talking about the splits. The splits are caused by nuclear magnets, and the nuclear magnet always has the same strength. And so no matter what the external magnetic field, the frequency difference between peaks of a split signal, which we call the coupling constant and indicate with J, remains unchanged. And so if we're looking at a 1 Hertz split, that 1 Hertz makes up a much larger portion of the 60 megahertz machine's signal compared to the 1 Hertz and a 600 megahertz machine. And so we're a lot more likely to get peaks overlapping when we have the smaller resolution machines. So here I'm pulling apart the same slide that I used in our last lesson. Now, if we look at the actual splitting, we see that the weaker the magnet, the more likely that complex splitting patterns won't be resolved. So if we look at I think it's a heptat on the top in the 300 megahertz machine on the far left. If we look down that column, we see that we don't actually see all those peaks well defined. Similarly, if we look at the 300 megahertz machine, you can see the peaks of the quartet. That's the second one from the right, or sorry, second one from the left. The peaks are really well resolved in the 300 megahertz. It's 4 very thin lines, and they get farther and farther apart as we have a less and less resolution instrument. So with stronger magnets, we end up having much better resolution between those peaks. It's important to recognize that on lower resolution instruments, we might not actually completely resolve every similar peak. So in this 3-hexanone, we see on the 90 megahertz spectrum, CH3s on either end of the spectrum actually end up overlapping. But if we move down to a 300 megahertz instrument, we see those same 2 CH3 groups completely resolved, both as triplets. Because coupling constants are based on the strength of the interaction between 2 nuclear magnets, the same interaction that's present with D splitting C should actually be consistent with what we see for C splitting D. And so if we look at the signal for C, it has a coupling constant of 7.6 Hertz. But if we look at D, it also has the exact same coupling constant. And so for many molecules, using the coupling constant can tell us a little bit about which protons are next to each other, not just how many neighbors. We know that C and D are next to each other because they have the same coupling constant. And we also know that B and A are next to each other because they have the same coupling constant. Coupling constants are predictable, so we can use a coupling constant table in the same type of way that we'd use a shift table. Most of the time, we have relatively significant coupling when we have hydrogens that are on adjacent carbon, on the order of 6 to 9 Hertz. If we have things that are farther away, we see no coupling constant. There are a couple of exceptions to that, though. If we have things connected across an alkene, cis connections are 7 to 12, like so. If we have trans connections, like this, we end up with an even more significant coupling constant because those actually are talking through the molecular orbitals. And if we have vicinal hydrogens, ones that are on the same carbon, those end up having actually a very small coupling constant. They seem like they might be otherwise identical. They're actually a little bit different because one's cis and one's trans to the stuff on the other side of the ring. Similarly, we have very small amount of coupling that's present if we have an aldehyde hydrogen and a neighboring hydrogen as well. We have larger couplings when we have things in an aromatic right next to each other, but we actually have a small amount of coupling that's possible within an aromatic, again because it's using the molecular orbitals to couple those magnets on the order of 1 to 3 Hertz. It's not as strong of a couple, but it's still there. And if we have para relationship directly across from each other, that goes down even further, but on a high resolution instrument, you still might be able to see a little bit of that. So we know that we can have different splittings that coexist. So here's an example where we have some things that are split to different magnitudes. On the last slide, we had said that when we have hydrogens on the same carbon, that's a double bonded carbon, we might have something that's a splitting on the order of 1 to 3. But if we have things that are trans, we have something on the order of like 7 to 12. And so those are really significant differences. If we know that we have both of those splittings, when they split, they're not going to overlap exactly the same. So if we look at HB and how that's splitting they're being split by HA at first, we have a very small splitting of 1.8 hertz. You can see that on the rightmost diagram. And then the second splitting is much larger. It's 7.1 hertz, and we split twice. Notice that now we have 4 peaks, but the 4 peaks aren't in the 1 to 3 to 3 to 1 ratio that would be predicted by Pascal's triangle, and they're not in a 1 to 3 to 1 ratio that would be predicted by 2 neighbors. Because the 2 neighbors have different splitting constants, we end up instead with a doublet of doublets, 2 pairs of 2 signals that are each 1 to 1. We can also have triplets of doublets. So we saw before that when an aldehyde is coupled to a proton nearby, that's a very weak coupling, whereas proton-protons on sp3 carbons are much stronger interacting. And so for this molecule, we'd end up seeing a triplet of doublets for the H2 on carbon 2. Now, a lot of times we might be able to resolve those on a high resolution instrument, but on a lower resolution instrument, we might not see any difference. So even though we have a slightly different coupling between these two and these two, they're both similar enough. They're both connected through a sigma bond on sp3 hybridized carbons that have mostly hydrogens on them. And so we don't actually practically see any difference between those couplings. And so those are going to overlap, and we'll see something that roughly looks like a sextet from the 5 neighbors. And we should have about the right distribution as well. Now, we're always looking at real data, and so it's not always the exact same height between the middle peaks, and it sometimes skews a little bit. But when it looks close enough to this ratio, then it probably is. We had talked before about how we could actually use different nuclei as long as the gyromagnetic ratio gives us a difference in radio frequencies that we can actually measure. Carbon-13 spectroscopy is a lot like proton spectroscopy. A couple of similarities include that we can measure shifts in parts per million. Even though the scale is larger on carbon-13 spectroscopy, we still do the exact same type of analysis. We know that inductive effects from electronegative atoms will always shift our signal downfield in the same way that they did for proton NMR, and magnetic anisotropy shifts also are going to be affecting the signals in a similar way. Now, here are some differences. We know that the frequency is about the 1/4 of the magnitude due to having a lower gyromagnetic ratio. So it's a lot harder to see that signal. The deuterated solvents are still going to get background. So even though we might be able to remove some of the signal by using a solvent that has deuterium instead of hydrogen, now if we dissolve it in a different solvent, we're going to see all the signal from that solvent. And carbon-13 is only 1.1% of the carbon that we actually see. So that means that normally our magnets aren't next to another magnets. They're only next to another magnets about 1/10,000th of the time. And so that means that we don't typically have any splitting, and we don't typically have good integration. We also, because we have less signal, tend to have a lot of noise in our spectrum. And so we take lots and lots of measurements to try to reduce that. In theory, we could still see splitting from protons, because the protons are magnets just like the carbon-13s are magnets. But that makes our spectra actually really complex, and for simplicity, we typically decouple the carbon-13 spectrum to remove the splitting. We essentially saturate all the magnets that are protons so that all the magnets are in the one state, and so that way we'll only see one peak for the carbon-13 spectra. There are shift tables in your textbook just for carbon-13 NMR, just like there are for proton NMR. So this is table 16-4, and we see the same types of changes. When we go from having one carbon attached to having more carbons attached, we see more shift. When we go from having something that's less electronegative to something that's more electronegative, we see more shift. We see kind of mild shifts on the carbons that are part of alkynes. We see more significant shifts from the alkenes because of the locations of those carbons in the direction of the magnetic field. And we also see relatively significant shifts from magnetic anisotropy around aromatics as well. There are other special forms of spectroscopy. One of these is called distortionless enhancement by polarization transfer, or DEPT spectroscopy. We can use different pulse signals to determine what types of hydrogen connectivities we have. So in DEPT spectrum, we might pulse at 90 degrees. So that's a phasing argument about what phasing we're putting for the radio frequencies. Or we might pulse at 135 degrees, or we might have just a normal spectrum. A normal spectrum shows all the carbon peaks straight up. In a DEPT 90 spectrum, we only see the CH signals. So that tells us right away which carbons only have one hydrogen attached. And on the DEPT 135, we end up having the CH or CH3 signals appear positive, and we end up with CH2 signals appearing negative. And so by taking DEPT 90 and DEPT 135 together, we know how many hydrogens are associated with every carbon peak. Now we've gone through 2 lessons on NMR. From the first lesson, we should have a general idea of how NMR works. We should be able to identify the number of NMR signals given off by a certain molecule. We should be able to use a shift table to identify approximate locations of the shifts. And we should be able to explain in general terms what's going on. Why are things more shifted? Why are they less shifted? Now, after this lesson, we should be able to predict peak area based on structure. So if you have more protons, we'd expect more peak area. And we should be able to predict splitting based on structure. If we have n neighbors, we should have n+1 peaks. And we should also be able to predict coupling constants given the structure using a table for that. Now, if we think about how we're actually going to use this most of the time we're using this to try to figure out what the structure of a molecule is. So the H1 NMR gives us a lot of information about how many different types of hydrogens there are from the total number of signals. It tells us the relative number from the integration. It tells us what types of things it's attached to, the environment. So is it near something electronegative? Is it aromatic from that shift? And it also gives us an idea of neighboring hydrogens from the splitting. Carbon-13 gives us some of that same information, but now about carbon atoms. So it tells us how many distinct carbon atoms there are and what environment there are. And we can actually get the amount of hydrogen atoms from each carbon as well if we need to. So let's think about what type of information we can get from an NMR spectrum. If we have a molecule with a formula C6H14, we have some idea about what that molecule might look like. We should be able to draw isomers of it. We can get a little bit farther if we know what the NMR spectrum looks like. So right here we have an NMR spectrum that has 2 peaks. I've zoomed in as much as I can so that we can see there's 1 equivalent here, so that 1 equivalent indicates the integration, and there's 6 equivalents over here. The 6 equivalents is a doublet. So the fact that it's a doublet tells us that we should have 1 neighbor. Big surprise, that 1 neighbor is over here. This is a heptet, which means we have 6 neighbors. And so we know that these 2 are next to each other. So we only have 2 types of protons. One has 6 possible and one has 1. The only way that the most likely way that we'll see 6 neighbors is if we have a structure that's kind of like this. This proton that's between these 2 other carbons, or this on a carbon between 2 other carbons, will be split by the hydrogens on each of those. We would expect to see it split 6 times because there's 3 on each carbon for a total of 6. And we should expect it to have an integration of 1 if there's only 1 proton here. Similarly, we would expect all of the hydrogens on the outside to have doublets because they're split only by this hydrogen. So that works, but we only have 3 carbons. And so we'd have the other molecule would have to be completely symmetric. Notice that we have these 2 hydrogens right here and right here that are giving us those heptets. They don't actually split each other because they are identical, in the same way that none of the hydrogens on this carbon split each other either. So this is the source of this. This molecule is the source of this structure. We can see the same thing in the carbon-13 spectrum. We see 2 peaks, both of them corresponding to carbons single bound to other carbons. And those 2 peaks are relatively unshifted. We know then that this structure that we drew on the last page should also work. We have essentially two isopropyl groups tied together. Each of those isopropyl groups has two carbons, two types of carbons. The ones that are on the end, the CH3 groups, and then we have the CH groups that are in the center. So these two are the same, and the other four are the same as well. So now let's think through another example. Here we have a structure that has C5H10O. Right away we have some idea of how many double bonds or rings we should have based on the units of unsaturation. We know that normally we'd have C5H12 if it was a completely saturated molecule, 12, not 13, and we actually only have 10. And so because of that, we should have one double bond or one ring, so one IHD. We also know that we have 6 equivalents of one type of proton, 3 equivalents of another, and 1 equivalent of a last. And we also know that the 3 equivalents has no neighbors. So that's most common that we have no neighbors when we have a CH3 that's attached to something that can't be attached to hydrogens, like a methyl that's off of an aromatic or a methyl that's off of, say, an oxygen. So that'd be one way that we could have that happen. And then we'd have the other carbons on the other side. So maybe something like this. Now we should have an H here that's split 6 times, maybe giving us a heptat like this. We also have the H's here and here. There are 6 of them that should split into a doublet from this. So this looks like it'd work. The problem is we don't have enough carbons, and we don't have any units of unsaturation. So we have to find a different way to keep these groups that both are good groups. We both have a methyl and an isopropyl, but we have to separate them. So we know that we have 1 unit of unsaturation. We know that we are missing a carbon. If we separated them by a carbon with a double bond to oxygen, that could give us our 1 unit of unsaturation. And then we'd have the CH3 here representing the 3 equivalents of that singlet. As long as we don't have a hydrogen directly on this carbon, that prevents it from splitting at all. And then we have the isopropyl over here with a hydrogen that represents this heptat, or the heptat represents that hydrogen, and these other 2 sets of 3 hydrogens represented by the 6 equivalents doublet split by the 1 neighbor. This is the carbon-13 spectrum for the same molecule, so we can use this to check our work. We can say that we have 1, 2, 3, 4, 5 carbons with a double bond like this, and we should expect to see these 2 carbons be identical to each other. They're the farthest away from the carbonyl, so they're going to be over here. This one is going to be here. It's got the more electronegative carbons than the hydrogens, and it's closer to the carbonyl, whereas this one should be over here. And then way on the other side, we see this highly shifted carbon representing the carbon of the carbonyl. Because it's bound to double bound to oxygen, that oxygen will significantly de-shield that carbon. So everything checks out. Now, I showed you this linearly, right? We solved the problem with just the proton, and then we solved it. Usually what I'd actually do is go back and forth between these two. So I might look at the proton, look at the carbon, try to see how many unique protons there are and how many unique carbons. If there are more unique carbons than protons, that usually indicates that there's a carbon with no protons, which is helpful information as well.